Hi, I'm Clara Fanjong. I'm a PhD student at Berkeley, co-advised by Mike Jordan and Jennifer Lisgarden. And today I'll be sharing our work on what we call autofocused oracles for design. This work was driven by the question of how should we be using data for design? And in particular, how should we train predictive models for the purposes of design? So to motivate our problem, data-driven design is becoming popular in all sorts of applications, from protein design to the design of new molecules and materials. And what I mean by data-driven design is the specification of novel objects with a desired property in a way that's learned completely from data. Now, for many of these problems, the data are not cheap. They require labor-intensive, expensive, time-consuming experimentation, which is very often a bottleneck. And as such, we actually focus on design when you have fixed labeled data. So our setting is completely unlike active learning or Bayesian optimization, where you can depend on new data coming in. So a common approach today is to train a regression model on the fixed data and use that model to guide your design. And we call that model the oracle. And the problem is that the oracle is only reliable on test data from the same distribution. So in this one-dimensional example, if your goal is to maximize the ground truth property, but you just maximize the oracle, all you're doing is finding where the oracle has greatest error. So this is the conundrum. We need to stay close to the training data so that we can trust the oracle, but we need to depart from the training data so that we can find something that's better than what we already have. And that's the tension at the heart of data-driven design. Now I'll overview how we formalized this problem. X denotes the inputs, Y denotes the real valued property, which the oracle is trained to predict, and S is the constraint set that encodes our design goals. Now, Y is a random variable due to experimental measurement noise, and the quantity that we want to maximize for design is this. It's the probability under the oracle parameterized by beta that the property satisfies the design goals given the input X. And finally, we frame data-driven design as a model-based optimization problem, which means that instead of maximizing this quantity over inputs X, we maximize over distributions p theta x over the input space. So p theta x is some generative model parameterized by theta, which we call the search model. To solve this problem, the good news is that there are a number of existing methods for model-based optimization. The bad news is, again, the oracle is not the same as the ground truth. So there's no way that solving the oracle-based problem on the right is guaranteed to optimize the true probability that the design goals are met, which is what we actually care about, but which we can't access because we only have fixed data. So this is where we started to think about design differently. The classic way of framing design is as an optimization problem where the search model theta is the variable, while the oracle beta is fixed. But what if we could also think about the oracle as a free variable? In other words, how should we select or train the oracle given that it will be used for design? And we propose to use the oracle that minimizes this quantity, which we call the oracle gap, because if the oracle gap is small, then by Jensen's inequality, the difference between the ground truth and oracle-based objectives is also small. So now we want the search model that maximizes the expected oracle output, but using the oracle that minimizes the oracle gap. And these two objectives are linked. So we've actually arrived at a non-zero-sum game rather than an optimization problem. And the goal of design is now to solve the game by finding the Nash equilibrium. To do that, we're going to take an alternating ascent-descent approach, where we alternate between updating the search model to increase its objective and updating the oracle to decrease the oracle gap. And we show that this can be accomplished by running any existing method for model-based optimization, but iteratively retraining your oracle with weighted maximum likelihood, where the data points are reweighted depending on the current search model. Now, this is a nice intuitive solution because it basically says that design induces covariate shift, so you should be constantly correcting the oracle to account for that. Now I want to briefly show how autofocusing improves outcomes for a material design problem. And the goal here was to design materials that maximize critical temperature of superconductivity using a fixed data set of about 21,000 materials. So here's an example trajectory of a design algorithm without autofocusing. The ground truth temperatures of the candidates at each iteration are shown in indigo, while the oracle predictions of those same candidates are shown in orange. And remember that the design algorithm only has access to the oracle. And you can see that the oracle predictions in orange are rocketing upward, but that the ground truth values are falling, which shows the design algorithm is being deceived and moving into regions where the oracle is no longer reliable. With autofocusing, you can see that the indigo and orange track each other and are correlated, which means that the design algorithm can actually trust the oracle to find materials with high ground truth values. So we saw this trend when applying autofocusing to 5 different model-based optimization methods. And we also saw that autofocusing provides statistically significant improvements to the final design candidates of all 5 of these methods. So to wrap things up, at a high level, our contribution is to note that design may require different inductive biases than traditional uses of predictive modeling. And here we reformulated design as a game, which allowed us to rethink how to train predictive models for design. And with that, I want to say thanks to all the members of the group who provided lots of great feedback and to the NSF for funding. And thank you for listening.